When anions form, they do so because the atom gains electrons, and so electrons get added to the electron configuration. Therefore, no, we can't look at that one because that's the other example. The opposite happens with cations. They're losing electrons, and so we subtract electrons. So for main group cations, if you're trying to write the electron configuration, you start with the atom, that's what it's called. You start with the atom and then peel them off in reverse order of filling. So you're going to take off this 3p electron first, and then the two 3s electrons, and you'll end up with this guy, which is equal to neon. And it's always a good sign when your boxes are full for your orbital diagram here. Full boxes, good thing. For the transition metals, it works a little differently. We ignore order of filling, and what we're going to do is we're going to remove the valence electrons first. So for iron has this electron configuration. We got 2p6, 3s2, 3p6, 4s2, 3d6. There's 3d electrons in here. Those were the ones that we think of as being added last. But when it makes an ion, we're going to lose these two valence electrons first. 4 is the highest principal quantum number. That's the valence shell. This has 2 valence electrons. So it's going to lose those first. When it loses those, then it has this electron configuration. And if we're going to make a 3+ cation, then we're going to lose one of these 3d6 electrons. And that's how we get 3d5. What do you notice about this block here? All the boxes are half full, right? And so there's some benefit in that, of having it be half full. And so iron can form a +2 ion or a +3 ion. And we have ideas or concepts of paramagnetic and diamagnetic. And this has to do with paired and unpaired electrons. An atom or ion is paramagnetic if it has unpaired electrons. That one bothers me because para sounds like pair, right? It makes me think that paramagnetic would have paired electrons, and that's not the case. Paramagnetic has unpaired electrons. A paramagnetic element is going to be attracted to a magnetic field. Have you noticed that not all metals are attracted to magnets, right? Magnets won't stick to your quarter. They just won't. They don't stick to aluminum. Aluminum is not paramagnetic. Iron is. Diamagnetic atoms or ions have electron configurations in which all the electrons are paired. So the way I try to remember this, at least, di means 2, right? Diamagnetic, there's 2 electrons. All the electrons are 2 by 2. Dielectric is a completely different idea. Diamagnetic, they're all paired up. These sorts of atoms or ions are actually slightly repelled by magnetic fields. They're not going to stick.
So that was when they're in the boxes?
That's where it's helpful to be looking at the boxes, yeah. So here we're going to write electron configurations and orbital diagrams for these 2 ions and predict whether they're diamagnetic or paramagnetic. So cobalt. Cobalt is, let's just do the noble gas shorthand version. So that's argon plus what? 4s2. And then those guys in the middle are 3D, and how many? 1, 2, 3, 4, 5, 6, 7. 3d7. Everything underneath is full. All those guys are going to be paired up, and so we don't really need to worry about those guys. We just need to worry about these guys. So here's our 4s box. And there's our 3d box. And this is where Hund's rule is important. So there's 2 in there. Oh, that doesn't show up very well. I wanted it to be different. There we go. And then the 7 in here will go 1, 2, 3, 4, 5, 6, 7. Does it have unpaired electrons? Yes, it does. Is it paramagnetic or diamagnetic? It's paramagnetic. So cobalt 2+ ion is paramagnetic. It will be attracted to a magnetic field. Let's look at N3-. Well, we should start with just nitrogen. So nitrogen is going to start off with helium, and then what? 2s2, 2p3. Oh, shoot. I made a big mistake in cobalt 2+. That's cobalt that I did. I didn't do the ion. Okay, so cobalt, the metal, is paramagnetic. How do we make it an ion? What electrons do we take out first? The 4s. So we need to get rid of those guys. I'll just put a 0 there. So that's taking these guys out of this box. And then, what do I remove? Nothing, because I'm done, right? Brain fart number 2. It's getting smelly in here. So it is still paramagnetic. That would be one of those exam questions where you made this big error, but you still got the right answer. It can happen. Okay. Back to nitrogen. So this is the configuration for nitrogen, but this is nitride ion. So 3-, do we subtract 3 or add 3? We add 3. So this isn't P3, it's P6. And if we draw the orbital diagram for the valence shell, we have 2s and 2p. And then we stick our electrons in there. There's 2 in there, and then 1, 2, 3, 4, 5, 6. Paramagnetic or diamagnetic? Diamagnetic. Everything's paired up in 2s. Diamagnetic. Any questions? When you make an ion, that affects the size. A cation is going to be much smaller than a neutral atom because with the cations, you're taking off the valence shell. You're peeling off that outer skin of the atom onion, I guess. The onion atom? I don't know. It's not an onion, though. It's an onion. Yes, thank you, Train. So we took the outermost electrons off. And because of that, there's an even higher effective nuclear charge. Because now it's the ones below that we're looking at, and they're being shielded by fewer. Let's just think about that real quick. Let's look at somebody small, maybe sodium. So sodium, it's got 1s2, 2s2, 2p6, 3s1. And here's our nucleus with plus 11 in it, 11 protons. When we make the ion, we get rid of this one. Well, actually, before I do that, what's the effective nuclear charge for this 3s electron? It'll be 11 minus the core electrons. There's 10 of them. So that has a Z effective of 1 plus. If I get rid of that guy, let's do that with a different color. If I get rid of him, what's Z effective for the n equals 2 electrons? It's 11 oops, didn't mean to do that. 11 protons minus the core electrons. What are the core electrons? It's just the 1s. So it's 11 minus 2. Now the effective nuclear charge is 9 plus. And that has the effect of doing this to the size. Here's the sodium atom, and here's the sodium ion. Taking off one electron doesn't seem like it would be a big deal, but it causes that cation to shrink a lot. So for all of these guys, the cation is much smaller than the atom. Does that make sense? Anions are bigger, and that kind of makes sense because we're adding electrons. But the change is not quite as dramatic. We're adding one or more electrons, but we have no change in the nucleus. So the nucleus, the effective nuclear charge is actually lower, which allows these guys to let out a little bit. So higher effective nuclear charge on the cations is causing the electrons to pull in and the ion to shrink. Here we're adding an electron with no change to the nucleus. Effective nuclear charge decreases, and that allows them to kind of puff up and expand. Isoelectronic means that the atoms or ions have the same, iso is a prefix that means same, the same electrons. So if we look at a series of isoelectric ions, here's sulfide, chloride, potassium, and calcium. All of these guys are around argon, right? Sulfur and chlorine are before argon. When they gain electrons, they get 8 electrons to become isoelectronic with argon. Potassium and calcium are past argon in the periodic table. They lose an electron or two to get 18 electrons. They're isoelectronic. They have the same number of electrons. The electrons are in the same arrangement because they always fill up in the same way. But look at the sizes here. Sulfide, 184, chloride, 181, potassium, 133, calcium, 99. This is much smaller than this guy, about half the size, actually, because of the increasing nuclear charge. So here we've got 20 protons versus 16 protons, and so that causes the size to change, become smaller. Okay, choose the larger atom or ion from each pair. Which is bigger, potassium atom or potassium ion? When we make a potassium ion, are we adding an electron or taking one away? We're taking one away. We're taking away the valence shell. We're taking the whole outer layer off. And then we're dropping down to the next level. Effective nuclear charge increases, so potassium atom is the larger. Fluorine or fluoride? Fluoride. We're adding an electron. So it's good to understand why the difference is so great. But even if you don't quite grasp that part, here we're adding an electron to it. It gets bigger when you add something. Here we're taking away, it's going to get smaller. So fluoride's bigger. How about Ca2 plus or Cl minus? So calcium ion and chloride ion are isoelectronic. They have the same number of electrons. They both have 18. Both have 18 electrons. How many protons does calcium have? 20. How many protons does chloride have? 17. Even without looking at core electrons, which one is going to have a stronger pull on these electrons? The calcium. There's 20 protons there. Actually, 10 of them are being shielded, but still, 10 are being shielded here, so it ends up being the same. So this has a stronger pull, a higher effective nuclear charge, so the chloride is going to be larger. Right? Let's go back. Chloride's 181, calcium's 99. So they all have 18 electrons. But they both. 8 of those are valence electrons, and 10 of them are core electrons. So if we take the actual charge on the nucleus minus the number of core electrons, we get an effective nuclear charge of 10 and an effective nuclear charge of 7. An effective nuclear charge of 10 causes the electrons to be pulled in stronger. Lower effective nuclear charge. This is like, mom who just doesn't have it together and her kids wander farther out in the neighborhood than mom who's more on top of things and is stronger about making her kids do what she tells them to do. So these guys are going to roam about farther and chloride's going to be larger. Any questions? Ionization energy. This was in that worksheet too. We often abbreviate this IE because ionization energy is a long thing to write out. This is the energy needed to remove an electron from an atom or an ion in the gaseous state. It's always positive. It's positive, meaning you have to exert energy to pull off an electron. You're essentially buying an electron from the atom. They are not paying you to take the electron. It's always positive. So if we take the metal, a metal plus the first ionization energy, we're going to get a metal ion with a +1 charge and 1 electron coming off. If we take that metal ion and put in more energy, that's called the second ionization energy, and that's generally going to be larger than the first one, and then we'll get a 2+ ion. And there could be a third ionization energy and a fourth. What we observe is that the first ionization energy decreases as we're going down a group. So here's the noble gases: helium, neon, argon, krypton, xenon. As we go down the noble gas group, the ionization energy becomes less and less and less. This is because those valence electrons are farther from the nucleus. Do you remember Coulomb's law? E equals Q1, Q2 over, is it R squared? Yeah, over R squared. So the energy, it's actually not equal, it's proportional. There's some constants in there, it's proportional. The energy of attraction depends on the magnitude of the charges. That's why a higher effective nuclear charge is going to have more force on the electron. It also depends on the distance. And so as we go down the group, the atom's getting larger. The electron that's getting pulled off is in a higher principal quantum level. It's farther from the nucleus. If R is larger, the energy required to pull it off is less. So ionization energy decreases. So, my chemistry land, politically incorrect analogy for this is, the Big Fresno Fair is going on right now. I have not been to the Big Fresno Fair for quite some time. I think it's humorous that they call it the Big Fresno Fair. Anyway, because I've been to some much bigger fairs. But anyway, I don't like the fair. I think the fair looks like an awesome place to lose children. Right? In fact, I think the last time that one of my children was there, they did almost get lost. I wasn't there. I let his uncle, and grandma take him, and they were very diligent in watching him, but they just, did not comprehend the magnitude of this child. So he hid from them under a table, and it was just very, yeah. I think that was Michael, yeah, actually. Anyway, so thinking about losing children. So I've got 6 children. I'm old. I'm tired. I really don't care that much anymore. But then I have a friend who struggled with infertility for many years, and they finally got one child. She keeps a very close eye on that one child. Now, do I love my children any less? No, but I am very distracted and distractible. And so, who would it be easier to snatch a child from? Me, right? My kids are wandering all over the place. They always come back. Sometimes I wish they wouldn't, but they always come back. But this other mom, she only has one child to focus on, and so she's always focusing on that child. Now, whether that's good or bad for the children is up for debate, but anyway, that's how it is. So, if we think of these atoms, helium, neon, here's xenon. Xenon has 54 electrons. Helium has 2. Who's it going to be easier to take an electron from? Xenon. How can xenon keep track of 54 electrons? Well, they're not really children, but you get the idea, right? It's a tool to help you remember the trend. So as you go down, ionization energy decreases. The first ionization energy is generally increasing as we go across a period. Because what's happening to the atomic radius? It's getting smaller. The closer that electron is to the nucleus, if the nucleus is mom, say, the closer the child is to mom, the harder it is to kidnap them, right? So the closer the electrons are to the nucleus, the more energy it takes to pull them off. So effective nuclear charge is increasing, the radius is decreasing, and so the ionization energy increases as we go across. Here's one of those cool tables that they make in textbooks. And so, of course, hydrogen, it has to be an exception to everything, but if we look here, we see generally, now there's some exceptions, but general trend, it's going up as we go across, and it's going down as we go down. Just based on periodic trends, determine the element in each pair with the higher first ionization energy. So tin or iodine? Higher ionization energy. It's going to be iodine. Iodine and tin are in the same period, the same row. Iodine is to the right. Ionization energy increases as we go to the right. Calcium or strontium? Higher ionization energy. Which one's bigger, calcium or strontium? Strontium's bigger. Who's it easier to take electrons away from? Strontium, because those electrons are farther out, then there's more of them, right? That's the way to remember it. So it's harder to take it from calcium because calcium's electrons are closer. This is actually how I think about it. It's kind of scary, isn't it? Carbon or phosphorus? Well, we need a piece of periodic table again. There's calcium, there's phosphorus. Going across calcium to phosphorus, which one would we predict being higher? Higher would be phosphorus. Going down, which would be higher? Carbon. So, we have opposing trends. So, can't tell. Not just by looking at periodic table. Only people who deal with ionization energies a lot would ever think of memorizing them. You look them up if you need to. That's why we have ginormous books called the CRC. It's full of all those things that you don't want to clutter up your head with. Most of the time, just predicting from the periodic table is good enough. There are exceptions. It generally increases across from left to right, but then we've got this exception between groups 2A and 3A. Boron has a smaller first ionization energy than beryllium does. What's happening is that boron is losing a 2p electron, which has a higher energy, and beryllium is losing a 2s electron. And so this higher energy electron is easier to remove because it's less stable. So let's look at the orbital diagrams. See, I put that in there because otherwise I wouldn't think to draw the orbital diagrams for boron and beryllium. We'll ignore the 1s2. So there's boron, and this is not the 1s. This is 2s, and, well, we'll just put 2p in there just for grins. And over here is beryllium. So we're just going to make equal diagrams for both of them. This is beryllium. How many valence electrons does boron have? Valence electrons. What group is it in? Boron, B. What's the B? Boron, 3, thank you. 1, 2, 3. How many valence electrons does beryllium have? Be, beryllium. We're all very tired. Just who get? Oh yeah, there's the yawn. There's the second one to go with the first one. Yeah. So when boron is ionized, we generally go in reverse order of filling, except for the transition elements. This isn't a transition element. This is a 2p orbital. These are higher in energy, and so they're less stable. Taking that off is not as difficult as pulling off a 2s electron. So there's some exceptions, but the quantum mechanical model helps us to understand those exceptions. Another one happens between 6A and 5A. Here, if we look at nitrogen, its orbital diagram, nitrogen has a half-full 2p subshell. And there's something special about half-full and completely full. There's an energy bonus in those situations. So for nitrogen, to lose one of these electrons is going to mess up this symmetry of being half full. Oxygen, if oxygen loses one, then it becomes half full. And that's kind of a good thing. So oxygen's last electron is having to share. It has to pair up. And so this one's going to be easier to lose than one of these guys. And then if we look at second, third ionization energy, there's some interesting things that happen. Each electron that's removed requires more energy. It's like, well, I sold you my first electron pretty cheap, but it's going to cost you more for the second one, and I'm really going to make you pay through the nose for the third one. But here, look at sodium and magnesium. Their first ionization energies, 496 kilojoules per mole and 738. To get the second electron off of magnesium, we've got 1450. The second electron off of sodium, 4,560. A lot more. What electrons are being removed? Well, that first electron is the valence electron that sodium wasn't real thrilled about having in the first place, right? The 3s1. It was keeping it from looking like a noble gas. That's removing the 3s1. The second electron that gets removed, where's that one coming from? It's coming from 2p. That's a core electron. That's a whole level below. Its ionization energy is going to be a lot higher. What about magnesium? Magnesium's first electron being removed is a 3s. And the second one is also a 3s. And then we see this really big jump when we go to a 2p. You see how that works? So here, removing one electron requires some energy, but not a ton, because that got to the noble gas configuration, and so this was good. But now, to remove an electron, we're screwing up the electron configuration of the noble gas. And so that's not a good thing, and so that's going to cost a lot. Here, magnesium, because it has 2 valence electrons, we can take the first one off, the second one off, and then we see this huge jump when we go into the core electrons. Like, you can take my jacket, but don't take the jeans, right? Because that would be much worse than someone stealing your jacket, right? Those are, trends in successive ionization energies. So what they're showing us here is where the jump is. They're showing us the pink is removing the first core electron. For sodium, which tends to form a +1 ion, it's removing the second electron that's bad. For magnesium, it's the third one, because removing the first 2 is pretty good. For aluminum, removing the first 3 to get a 3+ ion, not bad. Huge jump to the 4th one. And phosphorus. Now, we don't think of phosphorus as losing electrons, but how many valence electrons does phosphorus have? What group is it in? It's in group 5A. It's got 5. So the first one, the second one, the third one, the fourth one, the fifth one, there we've done all the valence electrons, and then huge jump to remove core electrons. I can't really remember why that table was in there, but it's mildly interesting, at least to me.